So how do we find the general solution of a trig equation? Now, what's a general solution of a trig equation, you might be asking? It's the solution that would cover every possibility. Now, with trig, there's always an infinite number of possibilities. I guess we've already seen it when we looked at the domain of the tan function, where we went plus pi on 2k, where k was some integer. And that described everywhere where the asymptotes were. Well, that's a generalized solution, so a general solution. So let's first of all have a look at sine equations then. So sine theta is equal to some number. Obviously, it depends on whether that number is positive or negative and how we approach the problem, because that'll give us different quadrants. So let's assume, first of all, that x is a positive number. Now, if x is a positive number, we know we could be in the first quadrant, and the size of the acute angle there would be whatever the inverse sine of x is, or we could be in the second quadrant. Now, that acute angle is still the inverse sine of x. So we'd have the first quadrant answer, inverse sine of x, but in the second quadrant, it's pi minus the inverse sine of x. So 180 degrees, but we're dealing with radians, so pi minus the inverse sine of x. So there's our two possibilities there for theta. But what if x is negative? Well, if x is negative, now I'm in the third quadrant. Inverse sine, the acute angle would be positive. So therefore, it's the inverse sine of negative x, because inverse sine of x in this situation would give us a negative acute angle. But we don't want a negative acute angle, we just want an acute angle there. So it's the inverse sine of negative x. And the same happens in the fourth quadrant. But once again, the acute angle has to be the inverse sine of negative x. So our third quadrant answer is pi plus the inverse sine of negative x, or 2 pi minus the inverse sine of negative x. Well, let's play around with that inverse sine of negative x. Remember, inverse sine is an odd function. So pi plus the inverse sine of negative x can become pi minus the inverse sine of x. And 2 pi minus the inverse sine of negative x becomes 2 pi plus the inverse sine of x. So there's our answers if x is negative. But let's just compare the answers from when we've got a positive number to a negative number. Because remember, we're going around the circle. And if we add 2 pi onto any solution, it'll be another solution. So our first solution when x was positive was inverse sine of x. If I add 2 pi on, I get 2 pi plus the inverse sine of x, which is the same answer we got when x was negative. And you'll notice the other answer is the same as well, pi minus the inverse sine of x. So what it basically means is, if we want to solve sine theta equals x, it doesn't actually matter whether x is positive or negative. We will always get inverse sine of x, then pi minus the inverse sine of x, 2 pi plus the inverse sine of x, and we could keep adding 2 pi to all our solutions. So the next one would be 3 pi minus the inverse sine of x. Then it would be 4 pi plus the inverse sine of x. So you notice how the inverse sine of x is alternating. Whenever I have an odd multiple of pi, I minus the inverse sine of x. When I have an even multiple of pi, I add the inverse sine of x. So how do I write that down? Well, I'm going to say theta will be equal to multiples of pi plus, now the negative 1 to the power of k will alternate between plus or minus. Whenever k is odd, negative 1 to the power of k will be a negative number. And that's what we said. We wanted odd multiples of pi minus the inverse sine of x. Whenever k is even, we'll get plus the inverse sine of x, and that's what we wanted. But we need to put a restriction on k. K has to be an integer. So k is an element of the integers. So that's our formal solution for a sine equation. It comes up with what we call a general solution. Let's do one for cosine then. We'll do it the same way. Let's assume x is positive. So in the first quadrant, we get the acute angle, the inverse cos of x. And in the fourth quadrant, that'll be the acute angle inverse cos of x. So my two answers, inverse cos of x or 2 pi minus the inverse cos of x. What if x is negative? Well, x is negative, we're in the second quadrant, but once again, it's not the inverse cos of x now, because x is a negative number. We want an acute angle. So we have to do the inverse cos of negative x. And the third quadrant, that'll also have an acute angle of the inverse cos of negative x. So my two answers, pi minus the inverse cos of negative x, or pi plus the inverse cos of negative x. Now, our rule for inverse cos of negative x, remember it was the one that was an odd function shifted up. So it's actually pi minus the inverse cos of x. So when I go pi minus the inverse cos of x, I just get the inverse cos of x. And when I go pi plus pi minus the inverse cos of x, I get 2 pi minus the inverse cos of x. The exact same answers that we got when x was positive. And of course, we could keep adding 2 pi to each of those solutions. So what does that mean for our answer? If I'm adding 2 pi to each of those solutions, I'm going to go inverse cos of x, 2 pi minus inverse cos of x, 2 pi plus inverse cos of x, 4 pi minus inverse cos of x, 4 pi plus the inverse cos of x, starting to pick up on a pattern. So if cos theta is equal to x, we're always going to end up with multiples of 2 pi plus or minus inverse cos of x. Once again, k has to be an integer. That's our generalized solution for a cosine function. All right, let's complete the suite. Let's have a look at what happens with tan. So tan, if it's positive, we're in the first quadrant. The acute angle is the inverse tan of x. And we're in the third quadrant. So I get inverse tan of x or pi plus the inverse tan of x. And once again, we could add 2 pi to each of those. X is negative. I'll be in the second quadrant, but again, I want a positive acute angle here, so it actually is the inverse tan of negative x. And then in the fourth quadrant, inverse tan of negative x. So I have pi minus the inverse tan of negative x, or 2 pi minus the inverse tan of negative x. Inverse tan, odd function. So inverse tan of negative x is equal to the negative of the inverse tan of x. So these become pi plus inverse tan of x, or 2 pi plus inverse tan of x. Again, we've ended up with the same solutions. And we could keep adding 2 pi to each of those. So what we've ended up with for tan is multiples of pi plus the inverse tan of x. And once again, k has to be an integer. So they are our 3 general solutions to trig equations. So now if I've got something like this, sine theta is root 3 on 2, but they're not specifying a domain for answers. So that means they're looking for a general solution. All right, for sine, pi k plus negative 1 to the power of k, the inverse sine of root 3 on 2. And you need to specify what k is, so where k is an integer. Inverse sine of root 3 on 2, we can work that out. That's pi on 3. So there's a better answer. Pi k plus negative 1 to the power of k times pi on 3. Now that is the formal answer. There is some debate as to whether the formal answer is in the course or not. And the answer is no, it's not. So what you can get away with if you don't remember these general solutions, you can simply do this. Sine theta is root 3 on 2. I know it's in quadrants 1 or 2, so I find my 2 answers, and then I simply say, hey, I can add 2 pi to each of these answers. But again, specifying what k is. So I could simply just write down pi on 3 plus 2 pi on k, or 2 pi on 3 plus 2 pi k. That answer is sufficient for this course. I show you the formal ones because I think it's important to know what the actual formal one looks like. But you won't be expected to know that one. Okay, let's have a look at the second one. Cos theta is minus 1 on root 2. Cos theta, well, theta is 2 pi k plus or minus the inverse cos of minus 1 on root 2. we can work out that. Inverse cos of minus 1 on root 2. Remember, inverse cos only gave us answers in the first and second quadrant. The range was between 0 and pi. So we're looking for the obtuse angle of 3 pi on 4 for that one. So 2 pi on k plus or minus 3 pi on 4. Of course, again, you could just do cos theta is minus 1 on root 2. So I'm in quadrant 2 or quadrant 3. So I put my two answers down and again just say, well, I can have multiples of 2 pi added onto each of these. I just keep going round the circle. Let's do a tan one. So tan theta is 1 on root 3. So my answer for tan was pi k plus inverse tan 1 on root 3, where k is an integer. Inverse tan of 1 on root 3, pi on 6. So we get pi k plus pi on 6. Or, it's good enough to go, well, tan theta is 1 on root 3. I only need one solution. So remember, the period of tan is pi, not 2 pi. So I can find one solution, which would be pi on 6, and then say for tan, plus multiples of pi. You'll notice we've got actually this time the exact same answer as the general solution. And k is some integer. All right, example 4. This is where a general solution can be very handy. Because here I can say, well, theta is, and using the general solution, pi k plus negative 1 to the power of k, inverse sine of the sine of 5 pi and 7. But remember, inverse sine can only produce positive or negative acute angles. So in this case, 5 pi and 7, second quadrant, I want the positive acute angle. So the positive acute angle would be 2 pi on 7. So pi k plus negative 1 to the power of k, 2 pi on 7. Cos 2x is cos pi on 9. Well, 2x, for inverse cos, it was 2 pi k plus or minus the inverse cos, the cos of pi on 9. Pi on 9 is an acute angle, so this one will just cancel to give pi on 9. But dividing both sides by 2, we end up with pi k plus or minus pi on 18. But again, you need to specify what is k, where k is an integer. Cos 4x equals cos x. 4x is 2 pi k plus or minus the inverse cos, the cos of x. Hang on. We don't know whether x is positive or negative. Well, if x is positive, the inverse cos of cos will just cancel, and I'll get x. So 4x is 2 pi k plus or minus x. Therefore, moving the plus or minus x to the other side, I now get minus plus x. So I have two possibilities. 3x is 2 pi k, x is 2 pi k on 3. Or 5x is 2 pi k, so x is 2 pi k on 5. Now what about the case where x is negative? What we need to keep in mind is that cosine is an even function. So actually the cosine of x is equal to the cosine of negative x. Thus, the inverse cos of cos x is equal to the inverse cos of cos negative x, and that will equal negative x, because remember, x is less than 0. So therefore, negative x is a positive number, and we said, well, when it was positive, inverse cos of cos will simply cancel. So what that means is if x is less than 0, 4x is equal to 2 pi k plus or minus x. In other words, exactly the same answer. So actually there is no need to consider the positive and negative cases for this particular question. So therefore my answers will be 2 pi k on 3 or 2 pi k on 5, where of course k is some integer. All right, let's have a look at this one. Sine 4x is equal to sine x. So using our general solution, 4x is equal to pi k plus, well, it'll be negative 1 to the power of k, inverse sine of sine x. Now, if x is greater than 0, inverse sine of sine x will just be x. Now I have to consider whether k is odd or k is even, because that'll change the value of the negative 1 to the power of k. If k is odd, 4x is equal to pi k minus x. So following that one through, x is equal to pi outside of 2n plus 1. I've changed it to 2n plus 1 because remember we're saying k is odd. So I want to ensure that we're substituting an odd number here. So that's over 5, where n is, again, some integer. Now k is even. Now 4x will be pi k plus x. It comes down to pi k on 3, but again, I'm going to change k. K has to be an even number, so we get 2 pi n on 3. If x is less than 0, look, same deal as we saw with cosine. We don't need to check positive and negative cases. Okay, so there are our two cases. Look, there's a handout in our notes on general solutions. Those last few examples, don't get too caught up on. I think it's way beyond the scope of what our syllabus is looking at. The main thing we need to take out of this, if they do ask us for a general solution, it is okay to find our solutions as we normally would between 0 and 2 pi, and then simply say plus 2 pi k, where k is an integer. For tan, we only have to say plus pi k because its period is pi. But anyway, have a go at these ones.